Uh, cool. So, as Mark mentioned, today's topic is how we use streaming SQL and Druid at Lyft to solve our problems. And I think I'm like really well set up for this talk because Gian already talked about how Druid works, and Max spoke about various challenges of ingesting into Druid, and this kind of addresses some of our efforts in solving that. So this is going to be our agenda for today. First, I'm going to talk about use cases and motivations. Then we'll go through the architecture, what it used to be, and what it is now with Druid in place. In that, I'll talk about how we use Apache Flink and Druid. And then last would be our conclusion. So use cases. So at Lyft, we have we are a very data-heavy company. A lot of people, like most people, use data one way or another. And on the left, you would see various kinds of users we have. We have analysts, we have data scientists, we have engineers, operations teams, executives. So all of them accesses data in various degrees. For example, an analyst's day job is to interact with data. Same is for data scientists. Engineers may be interested in different degrees in the data. They may be interested in trying to debug their service, or they may be pushing out new features, and they may want to look at the data to see the implication of the feature. Operations team, they are very, they're like our one of the most important teams to keep our business healthy. So operations team are responsible for different markets. So at Lyft, we have different geo areas, like San Francisco Bay Area, we have New York area, and we would have a general manager in that area, and they would be supported by operations team. And their responsibility is to make sure that the business is healthy. They have various tools and utilities to, shape supply and demand, etc. And they do rely heavily on the data to keep the market healthy. And executives, of course, they want to look at the data to see health of the business, how is our growth, and all these users accesses data using various methods. Some, for example, would be interested in dashboard. For example, an executive would only be interested in a dashboard which has been built by some data engineers or other folks. There's interactive exploration that you want to interact with the data. And sometimes people want to look at the data, writing SQL. SQL is quite powerful, and various users employs one or more of these methods to interact with the data. So kind of zooming in a little bit, certain use cases we have that we wanted to solve is, first is being able to look at real-time data. So recently in SFO, the airport, the pickup location for Lyft line was changed. For example, you can no longer wait near the gates. You have to go to a parking area to take Lyft line. So when it was rolled out, we are very curious, how it is affecting the market. Like how is it affecting the rides taken in SFO in real time? There are geospatial use cases. As I mentioned, GMs and operations team have a lot of levers to shape supply and demand. Let's say they employed a promo in a subregion, and they're very curious, whatever they did, whenever they deployed the promo, how is it affecting the market? Is it moving the metrics as we had expected? Anomaly detection. So let's say GM is responsible for a subregion, and if the conversion is low, a lot of people are requesting but not doing the right, or they're not able to find a match. How do you tell them that it is because supply is low in that area? There are not enough drivers to fulfill the request of the rider. So this is a kind of operational insight people want in real time, geospatially. You can also think of similar use cases for our engineers. If you deployed a service, you want to know how your service is doing. You deployed this new feature, you want to see how the market is responding to the new feature. So these were kind of like some use cases which were not satisfied by our existing infrastructure. So this is kind of our architecture before we had Druid in place. On the left side, you would see a box with various languages. That is basically to indicate various microservices we have. At Lyft, we have a microservice-based architecture. A lot of services written in various languages, and our data infrastructure is based on events. They all the services, whenever they come across some useful data, they would emit an event. It's called an event because always it will have a timestamp along with a lot of attributes. And we do provide a lot of SDKs in these languages to make it easier for our product engineers to emit event. So these are like our backend services emitting event examples. So, let's say the ETA service, whenever it gave an ETA to end user, it would drop an event saying I used algorithm X at time Y for user Z, and that will drop an event to our data warehouse so that we can kind of see the analyze on those information. We also capture user interaction at any point someone is using the mobile app. If they click on any button, if they, let's say the pickup location where they picked it by a pin drop or where they put an address. So all those things we capture. So basically events land into Kinesis from our internal backend services as well as from the mobile application. So Kinesis is a distributed queue from Amazon. It's a managed service. An open source equivalent is Kafka. So what happens is that from Kinesis, we import that data into S3. And as Max mentioned, at Lyft, we use Hive mostly to do data transformation. So we have our ETL defined and people express that in Hive query language. And the ETL process is basically, gather all these events and convert them into useful tables, usable tables, and we orchestrate that via Airflow. And people use, users at Lyft, they use Presto to interact the data, query the data, and at the end we visualize that in via Superset, be it in terms of dashboard, or like running SQL in the SQL lab, or just doing ad hoc analysis. That's the architecture we had at Lyft before we introduced Druid. Certain limitation, in our analytics database, only yesterday's data is queryable, so it's too late to get real-time data. Of course, we use Grafana, Elasticsearch, and custom application to track a lot of real-time metrics, but we did not have any platform solution for that. P75 query latency in Presto is 30 seconds. And it kind of goes back to what Gian mentioned earlier, is that if you want to interact with the data, 30 seconds is too late. You run a query, you would probably context switch because it's too long. You cannot just ask too many questions, iterate on that with that kind of latency. So the requirements to answer the questions I mentioned earlier is that we need data freshness in order of minutes. We need P95 query latency to be around few seconds, and geospatial is super important for Lyft, so we need very strong geospatial support. So with that, this is how our architecture looks like. Services and events goes into Kinesis, and we use Flink. Flink is an open source stream processor. I'll talk a lot more about Flink later. And the data gets ingested into Druid, which I'm sure you guys are familiar with now. And it gets visualized into Superset. I did not mention here how our batch ingestion flow works. Both Gian and Max mentioned that in Druid, you can ingest data two ways, in real time as well as in batch. We orchestrate the batch ingestion via Airflow. I'll focus more on the real-time ingestion side. Apache Flink, what is Apache Flink? So Apache Flink is an open source stream process, Apache top level project. It's a very scalable and performant stream processor. The APIs were heavily influenced by Google's data flow APIs. It has a very strong notion of event time processing, meaning, event time is a first-class citizen. It knows when data is late, and a lot of windowing function, etc., is based on event time. It has various layers of APIs. You can use functional APIs like map, reduce, etc. That if you use Spark, you may be familiar with. It has Stream SQL support, which is based on another open source project, Calcite, and it supports subset of ANSI SQL. And if these two high-level APIs are not good enough, you can always use direct API. So that's lower-level API that gives you access to Flink's internal state, and you can do like low-level work with that. So you have all these different layers of interfaces, and you can choose the one that's best suited to express your data processing needs. It supports joins, it supports windowing. And one good thing is that it also supports batch execution, meaning that the same logic you expressed and running in stream, you could choose to run it against S3 Parquet files, for example. Yeah. So next piece to solve this puzzle was Druid, which is today's topic. And why we choose Doit is it's a columnar database. It's very scalable. It keeps things in memory. It has a very good support for geospatial data. It is extensible. The APIs are super nice. It has a lot of like community contributed plugins, and APIs are it lets you basically drop in plugin for every aspect of the database. So it's a very it's a system that we can change to our needs. It also natively integrates with Superset, which is nice because that's what we use for dashboarding and analysis. And it supports real-time ingestion. So that's the reason why we picked Flink and Druid to meet the requirements I outlined earlier. And I'm going to go talk about how we use Flink Stream SQL and the reason we picked that to express our data processing. First of all, at Lyft, we use Hive SQL for all of our ETLs. So we are super familiar with SQL. Our data engineers and anyone that interacts with the data is already familiar with SQL. So it's nice that if we do the stream processing also in SQL, everyone would already be familiar with that. SQL also has very powerful, it provides very powerful semantics for data manipulation. Flink, as I mentioned, is nice because you can do streaming and run it also in batch mode. Another nice thing about Flink SQL is that you can extend that by UDF, so you can write user-defined functions at any point if you want to do some processing which was not already part of the SQL. You can always write UDF to extend the SQL capabilities. Another thing is join. This is super important because Druid supports very limited join, which is more like lookups. So Flink's streaming in front of Druid gives us a very nice way to pre-join the data before you can ingest, thus making our tables more usable for our end users. And I'll talk about few UDFs that we use at Lyft. So GeoHash is one. GeoHash basically is a way to encode latitude and longitude in one string. So it basically converts 2 dimension into 1 dimension. At Lyft, we have our definition of region. For example, San Francisco region, you have defined Lyft what polygon it is. And we could basically get region given a latitude and longitude that we usually collect from all our mobile events. Another is URL cardinality reduction or normalization. So Max spoke how Druid keeps data in memory, which is super fast but also expensive. So it's important that we are very careful and mindful of what kind of data we are ingesting into Druid. And in this case, you notice that certain URLs have very high cardinality because, for example, it has the user ID in it. The number of these URLs per day isn't, it's like many millions, and combine that with many other dimensions, the number of records per day becomes billions. So this is one technique to kind of reduce the cardinality. What we do in the stream SQL layer with the UDF is that we convert the string that looks like a hash to a string that says hash. So that way, the cardinality is under control. We normalize URLs where we remove slashes, etc., so that even if you have different strings with slashes, they would all end up finally being one string in Druid world. We do user agent parsing, for example, to get the OS name, OS version, app name, and version from the user agent. Sampling is another thing, like having this stream SQL layer in front of Druid makes it super easy for us to do sampling. As Max mentioned, like if you want to do sampling on user ID or other attributes, we can have UDFs to express that sampling very nicely. And this helps us employ various techniques to finally reduce the amount of data in Druid. This is not super readable, but this is what Lyft's Druid spec looks like. So if you're familiar with Druid specification, you would notice this is kind of document in a Druid. This is how you ingest data into Druid. You basically have to tell the table name, which is the data source. You say how the data is formatted. In this case, it's JSON. You also say what's the timestamp column. What we added here is something called expression. So this expression is basically a SQL snippet. And what it does is you are basically expressing how you want to transform a column. In the first case here, you would see that we have a case statement that if request path is null, do nothing with that. But if it is not null, then normalize that request path. And that's the UDF I mentioned earlier. On the bottom one, we are actually extracting the OS name from the request user agent. And also, just let me talk about what Envoy is for Lyft. So Envoy is an open source network, like service mesh that is used very widely at Lyft. So any service that talks to each other goes via Envoy, as well as it acts as a front proxy. So at any point, if you use the Lyft app, it basically hits Envoy load balancer. So given all service-to-service communication happens via Envoy, Envoy knows exactly how each service is doing, if any service is throwing 500, 400 HTTP error code, and we want that data in Druid for engineering debuggability. And this is basically how the transformation happens on Envoy log before it gets into Druid. The reason that this transformation is important is the Envoy log is huge, it's massive, like we have billions of records per day. And these are kind of data reduction techniques we employ just to make sure the data is under check and it's super fast to query at. So from that Druid specification, one more thing. So this is also like, basically this is where also you specify in Druid what are dimensions and metrics. And so basically it's a combination of Druid configuration as well as what kind of SQL transformation you want. So from the Druid spec, what we do is we extract the SQL statement, combining all those expressions. And this is what the SQL statement looks like, that we are interested in occurred at time, request host port, various columns, and we want to apply some UDF on certain columns, like we want to normalize the request path. We want to extract OS name, OS version, etc. from the user agent. And we want to do this from the topic Envoy HTTP access. So tying all of these things together, this is how our data flow looks like. Services logs event in JSON format, which goes to Kinesis. Flink reads from Kinesis, and runs the SQL on top of those streams. And it, as of now, uses the Tranquility lib to push that to Druid. And our data itself is defined in protobuf schema. So protobuf is basically how you describe our data. As of now, though, we don't use protobuf as the serialization format. We use it only to describe the data. And it helps that all of the systems are very type aware. They can check that data. They can do validation and make sure the column name types are as expected. One aspect is that, like at Lyft, we have many events. For example, Envoy was one kind of event. The total number of events we have is close to 1,000. And we, as the platform team, actually, it's very hard for us to make sure that we understand all the events, apply the right transformation, figure out which one is dimension and metrics. So we actually rely on our users who has created those events to configure how it should be ingested in Druid. So ingestion spec is the one that I showed earlier, is how you express that. So we wanted to build a framework where doing that is super easy. We put that in GitHub so that it's source control. You can get it reviewed by teammates. When you create a PR changing either a SQL statement or other aspects of the configuration, we run some test compile time validation. Like we make sure the SQL is correct. It has the column names as it's in the protobuf schema. You are using the right data type, like you are applying integer functions on integer, string function on strings. So all of these things run when you create a PR. And if there's any error, the PR would fail. So if the pull request succeeds, you have like good amount of confidence that it's gonna work. So this just helps our users to configure how they want the data in Druid, so that it's more scalable versus we as data platform doing that for our users. We also run integration test on the sample data. So this is basically a nice way of making sure that if your PR succeeds, it's going to work when you deploy to production as well. So finally, this is how you actually explore the data. So this is an example of the Envoy access log I was talking about earlier. In this chart, like I'm using, this is the explore view of a superset, which is the data exploration tool we use at Lyft, which is again open source. You'd see that I'm trying to figure out some issues with the service. I was interested in driver app. I was looking at when our service has returned status code greater than 500, which indicates it's an internal server error. I was looking at services like TCS and legacy API, and I wanted to see which part was responsible for that. And you can see a spike in here, like at around 1017 for API v1 config. So this is kind of very nice that I know which service and which endpoint had problem at the time, so that I can go and debug further and figure out what the bug is all about, why we threw internal server error. I showed our HTTP access log, but you can think of similar workflow for our operations and GM folks. Like the use cases I mentioned earlier, the questions they want to ask around market health and all, they would basically use similar flow to get their answers. So that's kind of what we have so far. And what's up for next is that we are moving away from Kinesis, and we have started to use Kafka. So so basically, Kinesis would get we'll use Kafka instead of Kinesis. So far, we are using JSON as the wire format between services, which is not very efficient in terms of parsing type safety. We want to use protobuf as the wire format as well, which is super efficient to parse. We'll continue to use Flink as the stream processor in front of Druid. But as of now, using the Tranquility library of Doit to push from Flink to Druid directly. but actually Druid plays nicer if you let Druid to pull from Kafka. It has better guarantees around that, meaning that like data loss exactly once, semantics. It basically Druid plays much nicer with Kafka for real-time indexing. So we're gonna move towards that. We will continue to use protobuf to define a schema, which all of these services would use the schema. So this is kind of our goal that we are aiming for, is that we want all events in real time in Druid, be it our operational data, be it our business data. We want all of it in Druid. Basically, if you log an event, we want you to be able to find that in Druid in real time. So Max covered a lot around how you should model data in Druid, and that's kind of one of the things we have to solve because data modeling in Druid is not trivial. You have to do a lot of iteration to figure out what should be a dimension, what columns you want. Is my data bloating? Am I ingesting too much data? So, and given we have a lot of events, we want to be able to come up with some reasonable default, like automatically figure out the Druid specification. And we're thinking of doing some offline analysis of our existing events using Presto to see, like, for example, cardinality of columns, which one's a string, which one's an int. Strings usually end up being dimension, to come up with reasonable defaults so that all the events we have, we can ingest with some default configuration and let our users iterate on that to basically get to what data they want. But like we want to make sure that at least some data is always there they can look at, just to incentivize them to use the data, modify it, and finally get to a data that's like they find it super useful. Another thing is auto provisioning of various resources. If you look at this flow, there are like multiple pieces. Like we have Kafka, Flink, Kafka, Druid. So how do you provision all of these things in a nice way that you can specify one configuration will all be taken care of? So the conclusion, we find the Flink streaming SQL in front of Doit is super powerful. It basically augments Druid capabilities. It lets us transform data before it gets into Druid. It lets us do join before we ingest into Druid. It lets us do sampling if you want to reduce the data set. So it's very nice way. Basically, I feel Flink, streaming SQL, and Druid combined is very powerful way to make data available. Easy to use ingestion framework is super crucial for adoption. Unlike Hive and Presto, in Druid you have to ingest the data, and for that we need super easy to use ingestion frameworks. Some challenges and next items. Druid needs, like, as of now, it doesn't have a lot of guardrails. We want the Druid user experience to be very predictable. So, just to make sure that people don't write queries which are not predictable, ends up taking a minute. So we need good retention strategies. How do you do that? Should that be size-based? Should that be time-based? How do you automate those things? Rate limiting queries so that everyone has a guaranteed user experience. We haven't yet done Flink batch ingestion. Let's say in the stream SQL you had a bug. How do you, backfill using the same configuration, same SQL statement? Anomaly detection, telling people if something is wrong. Root cause analysis, if something is wrong, hinting people why it's wrong. So these are kind of things we want to tackle as we go. Cool, so that's all.
You don't just get tied to Java software frameworks and structures. One of the things rate limiting is the
Okay. Yeah, so I think
5 milliseconds is nice in Java when you're only doing a billion deltas, but as soon as you start doing real machine learning and real AI analysis of that, moving it around the world, you realistically are doing 30, 45, 50
Yeah, so this is actually kind of, and this is for analysis, not like web service kind of communication.
Basically, with 5 milliseconds, it's not that fast. Next to speaker, you can't keep eventually consistent your AI and analytics with the new data coming in. You'll never be able to catch up. So that kind of is an admission. How expensive is it in memory for you guys?
So I did not quite follow your question actually.
How expensive, performance-wise, is it in memory for you? Are you seeing 40-50% success? Are you seeing faster? Do you have your own compiler or what?
Sorry, I did not follow your question actually. Sorry about that.
Okay, how expensive is your in-memory performance? You said it was expensive.
So it's a function of the data, right? Like,
Yeah, it's all.
yeah.
So what's that mean?
Like in-memory expense, do you mean like time taken or do you mean like cost, like how much we spend on it?
That's what usually in-memory expense means.
Yeah, so yeah. Yeah, sorry, if anyone else has any other question? Hey, yeah. So no, actually that's not because of Druid integration, but like Kafka we feel is a better pub-sub model. Like Kinesis, for example, has, it's not a true one producer, many consumer kind of model. They do have limits on how many reads you can do, how much read throughput you get. So basically, we had to employ like fanning out, etc., which I think Kafka is a better fit in terms of one producer, many consumer. Yeah.
All right, please give it up for Arup Malakar.